on the last lecture. So like I said, PDEs, the main technique is separation of variable. Yesterday, I've gone through one example in very detailed steps of all the new parts. So yeah, if you read the lecture notes, so hopefully my lectures is trying to make it easier for you to read the lecture notes. So you'll see all the examples for heat equations and Laplace equations as well. The only other thing I think you might struggle with is the part of the chapter that deals with inhomogeneous boundary conditions. And I'll display that part now in the first half of this, and then complete example. We'll see how much time we have. Okay. All right, so so I'll write a little bit lower. This is extra comments to help you with 7.6.1. So this is an example to deal with inhomogeneous boundary conditions. Okay, so this time let's do a heat equation. Let's this. So the question might start with saying, find the temperature of a rod. Okay, the temperature of the rod may be, it will use U like that. Okay, so a rod is probably one dimension like this. So U would be the temperature of the rod from 0 to L. Okay, so we are going to use this as the x-axis. And so if the temperature can be different, let's say a metal rod, so the temperature may be different. Of course, if you're an electrician, it might be a electric potential gradient across a wire or something. But I'm going to stick with this application. Right, okay, so yeah, so the temperature, this describes the temperature. Okay, and what else do we need for the function, for the domains from 0 to L, for this interval, and t from 0 to infinity. So now you can tell what is the space-like variable and the time-like variable. It's pretty obvious usually. And the differential equation is this. So I think, like I said last time, this kappa is going to, this kappa, it could have been a K, but people want to be fancy and use Greek letters sometimes. Yeah, it's a constant. To really describe something physical, that the heat will diffuse out, and instead of imploding, this usually will come out negative, but it doesn't affect any mathematics. From a mathematical point of view, it's just a constant. And of course, we need boundary conditions with it is both. Kappa should be positive for it to be physical. But anyway, like I said, mathematically it doesn't change anything. I was thinking the negative sign somewhere else. But yeah, sorry. Fortunately, mathematically it doesn't change anything. Yeah, I could have just kept it as these two as just for mathematics. I can just keep this as L and kappa as a variable, as a unknown constant. But let's make it something more physical. And the boundary conditions are such that yes. So now when I write this out, have a think which ones are initial conditions and which ones are quote unquote boundary conditions. So let's make sure we have all the ingredients. We have the function of interest. We have the domain of validity. We have the PDE itself. And we have these boundary conditions. Okay, so now let's actually check that. This is a comment on at time equals to this. Yeah, so this is a comment for when time equals to 0. So we consider this initial condition, and these are comments. This one is a comment at x equals 0, and this is a comment on the temperature at x equals to 1, right? Or L. Okay, so these are the boundary conditions. Again, this is semantics. Mathematically, you can just call everything boundary condition, but it's, give it a little physics meaning, physical meaning, then that is what it is. Okay, this is the question itself. Any questions about the question first? Okay. Yeah, so just to interpret this a little bit, yeah, in fact, let's interpret this a little bit, is I'm keeping the temperature, the boundary conditions over here at x, these are for all time, okay? Remember this symbol means for all. Okay. The upside down A or with a slash. At least for all time that is relevant in the domain of relevance, domain of validity. So at x equals to 0, we always keep it as at the temperature at -1. And of course, if you're really doing physics, you have some units in Celsius or whatever. Yeah, we'll just treat it as mathematics, right? Over here, we keep the temperature at 3. So it's very cold over here, or a little bit cold over here, a little bit warmer on the other end. And here, this at time equals to 0 for all x, right? So this is implied. Sometimes we'll write it out as part of the question explicitly, but usually it's implied already in the domain of validity that for any x, so that means within the domain of validity, for any x, we keep the temperature at 1 at time equals 0. Okay, so I'm just adding some interpretation. At time equals to 0, the whole temperature, the whole thing is 1. But you stick a block of ice over here, and maybe you put you start a candle over here. So so as soon as time starts from 0, the whole thing may start off uniformly with uniform temperature 1, but then suddenly this side is cold, this side is hot. So you would hope what we'll hopefully see is we'll find the full function as a function of x and t to describe how it diffuses, how it adjusts to these boundary conditions. Does that make sense? It's interesting also to dissect the heat equation a little bit. So I won't write everything in too much detail, but just sketch a graph for you to understand. So the heat equation itself, this is the heat/diffusion equation itself. It's actually quite easy to understand why it is in this way. Because let's say this is the temperature, and this is some x, some one-dimension space. Let's say the temperature initially is very fluctuating. Why forget about the boundary conditions? Normally, if ignore the boundary conditions, if your temperature is very fluctuating, normally how heat would do is it diffuse, right? So it's also called diffusion equation. So over time, you would expect heat to just equalize. Now let's see over here. Let's pick a point over here. This is a low temperature at this particular x. What does du dt mean in physics? Rate of change with respect to time is like speed, right? Okay, so it's how much U changes with time. If U increases with time, then this will be positive. If U decreases, so if the U gets colder and colder with time, you would expect this to be negative. How about d2u dx squared? What does that represent physically? Second derivative with respect to space. Right, yeah, is there a physical word for it? Someone said acceleration, but acceleration will be ddt with time, then it's acceleration. ddx is with space. What is one derivative with space? The slope. The slope of the graph, right? Temperature with space is the slope of that graph. And second derivative is the, starts with the C. Curvature, yeah. Curvature or concavity, right? I think Americans and British call it differently, but yeah, either concavity or curvature. So how concave it is. So here it's concave up, which means the second derivative over here at this point, uxx is positive, right? Uxx is positive, and what happens to the speed of the temperature? The speed is saying at this point, it's trying to increase the temperature. The rate of change of U with respect to time is positive, right? If I have a K that is positive. So that's why this signage does make sense. So sorry, completely flipped it around yesterday. But yeah, so this graph, you see this happens. And if I pick this point, now this point is concave down, which means that uxx, the second derivative with respect to x, is negative over here. Assuming this constant is positive, this tells you like how much it is, right? It's a proportionality constant. Then the u is trying to decrease it. It's trying to decrease the u. So you see over time it equalizes. Does that make sense? Okay. So this equation first came up by Newton as well. So sometimes called the Newton's law of cooling. But so all those heat equation, diffusion, nowadays we just write heat equation. Okay, right, so that's the interpretation. Okay, so before we jump into the separation of variable, we need to pay attention to the boundary condition and see that which one is the Sturm-Liouville problem, right? Because once we separate it into x and t, we need to choose which one to solve first. And we said we need to solve the Sturm-Liouville version first. So you see the boundary condition is usually the Sturm-Liouville one. And also the one that is bounded, not unbounded. But this is not the Sturm-Liouville boundary condition. If you go back to chapter 4, so I'll just write a few comments in bullet points. So normally it starts with the variable that gives a Sturm-Liouville problem, which in this case is x, but the boundary conditions is not Sturm-Liouville boundary condition. Forgot what that means. Look back into the chapter 4. We need that to be 0 with a Sturm-Liouville boundary condition. Okay, and that's not 0. So this is how we'll need to deal with it. So this is it's not Sturm-Liouville or AKA not homogeneous boundary condition. So if the proper boundary conditions is you need the right-hand side to equal to 0 for the boundary conditions as well, but this is not 0. Right-hand boundary conditions for x, right? Right-hand side boundary conditions for x needs to be 0, but it's not. Okay. I would consider this sort of the most advanced thing in the chapter to need to deal with that additional bit. So usually if this appears a little bit of exam tip, if this type of question appears in exam, first of all, it's going to be rare, but if it does appear, we will have part A, part B, part C to guide you through how to first change it into a homogeneous one, a Sturm-Liouville, and then we leave the rest for you to solve it. So once it is you have the Sturm-Liouville problem, you should be able to solve Sturm-Liouville problems. Okay, all right. So yeah, in exam there will be a guide, but I'll show you how it works. Okay. Okay. So what we'll first do is show what the comment is. Need to first change to a change of variable. Okay, and the tip is to look at the final or steady states. Okay. So let's think about it. If my temperature with space is at x equals to 0, I'm holding it at -1. And at x equals to 1, or L, I'm holding it at u equals to 3. Right, so like this. My starting point is here. So at time equals 0, it's like this. So this is the time equals to 0 solution. But what happens to the final state? So what happens if t goes to infinity? Well, even though at time equals to 0, it starts off like this, but if you continue to hold it until eternity, with these two boundaries at 3 and -1, you would expect as t goes to infinity, this is going to be a final solution, right? So this is going to what we'll call it, let's call it the U steady state, or the steady solution, or the final solution. So U steady is it's only a function of x. And so how would this look like? U steady is going to be, what's the y-intercept? Y-intercept is -1, and the gradient is 4. Okay, so I should say slope, 4x minus 1. So this is the U steady. I'm going to put a bar on top so that I don't need to write steady every time. Every time I put a U bar, it would just be the steady state solution. And then, so now we can let U of x t equals to the steady part plus the transient part. So I'm going to call this is the steady part. This is the transition part. So it's the transition. Sometimes people call fluctuation steady or final. Right. Okay. The steady state solution only depends on x because the time is at the final state, right, at infinity. But the transition obviously depends on t as well. Otherwise it can't transist. Okay. Yeah. So we'll say that at the end of the day, after the transition, this guy should be 0. And when time goes to infinity, you would just equal to this final state solution or a steady state solution. And to say this one more time, I'm just using this notation like U bar to denote this so that I don't have to write subscripts and fine prints every time. Like that. Okay. So in this case, we deduce the final solution is 4x minus 1. Okay. And in fact, U bar, the lecture notes doesn't use U bar, they use theta. So yeah, also maybe it's up to you with a choice, but I'll change it to theta over here, half of the reason to match the lecture notes, and half of the reason so you don't confuse the U and the U tilde. So now, instead of solving for U, let's try to solve for theta, for the transient function. Any questions so far? Okay, so now the PDE would look like. So originally the PDE is for U, right? So this side is U with one time derivative. So let's do a time derivative, but this guy would drop out because there's no time over here. So U with respect to time once, it's just theta with respect to time. Be clear, it's 0 plus theta with respect to time, right? Just to be very explicit. And how about U double X? U double X, this one will also disappear. So it will be 0. Even though there's an X, it doesn't support two derivatives. And then theta would just be applied over there. So the PDE is now the same. You'll see that the PDE is unchanged. It's still, therefore the PDE still reads exactly the same as the original U. Okay, that's interesting. Does that mean we just waste our time because the PDE is exactly the same? But no, our ultimate goal is to look at the boundary condition, right? So now let's look at the boundary condition. So let's start with boundary condition 1. Actually, boundary condition 1. Actually, I'll start with boundary condition 2. So just to see that we actually did what we want. Just leave the space over here. So boundary condition 2 is this. Now, U of 0t means x equals to 0. Right, so U of 0t needs to be -1. 0t needs to, we want it to be -1. But U of 0t is -1 plus theta of 0t. Right? And then now you realize you can cancel out both sides, and theta of 0t equals 1, 0, 0. So this is our modified boundary condition 2. And let's look at boundary condition 3. Originally, it has U of 1t equals to 3. So let's plug in U of 1t. U of 1 is 3 plus theta of 1t. So I plug in x equals to 1. And if I want that to be 3, this implies theta 1t equals to 0. And you see, magically, basically with this substitution, or I have maintained the exact same PDE while magically made these two 0. It's not so magic because theta is the transient function. It's just saying at the end of the day, at the boundaries, it's not going to transist because there's no transition at the boundary. The boundary is fixed. So we just basically split out the steady state and look at the fluctuations on top of that final state. Boundary condition 1, just for completeness, we'll put this here as well. So it's u of x0. I just erased it, but it was u of x0 equals 1. And so u of x0, let's plug in u of x0. So that means theta of, so 4x minus 1 plus theta of x0, we want that to equal 1. Okay, so that means theta of x0, we want that to be 2 minus 4x. Okay. So it does also change the initial condition a little bit, but that's okay, and that's perfect. Okay, so now this is the only new part to this. Basically, now our new goal is to our new function of interest is to solve this. This is my new function of interest. Right function. New function, and the domain. Right later. The PDE. Boundary condition 1, boundary condition 2, boundary condition 3. I don't have 4 boundary conditions because I just need 1 boundary condition for t and 2 boundary conditions for x. That's it. Right? The domains actually are the same as well. The domains are, because the functions is still a function of x and t, so the domains are still exactly. Any questions here? Okay. If we are happy with this, then it's just the rest of the 15 minutes. It's just then the same procedure as yesterday, and I'll walk you through it. Okay, so now proceed to solve theta of xt. Okay, so we do the standard. I'll just sort of segregate this out. Let theta xt equals to capital X of the variable x and capital T of the variable t. And let's see what happens to the boundary conditions. So the boundary condition 1 is now x equals to anything, t equals to 0. So it's just theta. So now it's theta of x0, which is the same as x of xt of 0 needs to equal to 2 minus 4x. Boundary condition 2 is basically x of t equals to 0. Boundary condition 2. Boundary condition 3, well, yeah, the modified one for theta is x of 1, t of t equals to 0. Okay, so these are my 3 boundary conditions. We can divide by this. So just look at these, and that's fine. So basically, it's x of 0 equals 0, x of 1 equals 0. So now we have a proper homogeneous boundary condition for x, exactly what we wanted. Right? Because remember the original goal, the whole original goal is we are hoping to start with the variable x, but the boundary conditions are not homogeneous, which means it's not a Sturm-Liouville problem. You can't really get the eigenvalues and eigenfunctions for x. And we went through these 3 slides to do a change of variable. We change the variable from u into theta, and now my x, this would be homogeneous boundary conditions. And then we'll solve the initial conditions separately. Okay, so once we've let this, the PDE is now. So for this one, right, x of t on one side is dbt, the other side is the kappa is 4, and then the 2x of xt. We go through the same argument where t is the only thing differentiated, so x comes out, and then you just have one derivative on t. And then here the t comes out, and you just have two derivatives on the x. And then now you divide both sides by xt, so you get t dash over t equals to 4 x double dash over x. This is the beauty of using capital X and capital T instead of like little f and little g, because now I can say these both should equal to a constant, which we'll call lambda, because that is a pure function of t, and the right-hand side is a pure function of x. And the fact that they can always be equal for all the domain of validity, better have both sides equals to a constant. Okay, so now I have two equations. The first equation is t dash equals to lambda t, and the second equation is x double dash minus lambda over 4 x equals to 0. Call this the t equation. We'll call this the x equation. So now, which one do we start with? Yeah, I'm going to skip like algebras of moving variables around. So outline just the key steps. Right? In an exam, these algebra maneuvers, feel free to skip. Yeah, let me make a 30-second comment about exams. A lot of times students don't know which steps you should write and which step you should skip. Sometimes it is the thing, oh, why do I, and students write out the steps that educators think you can skip, students don't skip, and then the things that we think you should show, students don't show. It's a mismatch in the understanding. So to clear up the misunderstanding, the general rule of thumb is very simple, is anything that is, any steps that is a new concept you learned in this module, you should show. Any step that you learned in A-levels or below, if it's things about moving algebra around, if you are comfortable with algebra, and you can skip as much as you like for algebra, I don't care, even integrations, solving a simple harmonic equation, that is something from year 1, even for undergraduate year 1. So anything before this module, if you're comfortable, feel free to skip and show only every 3 or 4 steps. That's fine. But if you're not comfortable, please show that, right? Because then you get partial marks if you made a mistake. Okay, then it's just a strategic thing that benefits you. And also, the more steps you write, the less chance you make a mistake, because you can see it. But from an educator point of view, I don't care about things you learn in year 1 or below, or A-level or below. But anything that is new, sometimes students think, oh, this is such a simple step. I'm not going to write this, right? Or like whatever is done, I'm just going to suddenly just chunk this appear. And now, even though this is a simple thing, it doesn't take brain power, but that's a new concept. So that's what we want to see that you've learned. So this is a general rule of thumb. Of course, yeah, it will take me a long time to go through what exactly, it's almost impossible to go through what exactly to show and what not, but usually this rule of thumb it works 90% of the time. Okay, right, so this is, yeah, algebra, that is the reason why I'm skipping that. And for the same reason, I'm going to directly solve this, because this is a simple harmonic equation. So we're going to start with the x equation. And now it depends on whether lambda is, it depends on lambda whether it's larger than 0, smaller than 0, or less than 0. So if lambda equals to 0, the general x solution is ax plus b. If lambda is 0, if lambda is larger than 0, the general solution is cosh and sinh. if lambda is less than 0, x is cosines and sines. This time I remember the minus sign. And like I said, some textbooks are being very smart. In the beginning, when they set this to a constant, they already set the constant to be negative of 4 lambda squared. if they're so smart, then this you won't have this ugly thing over here. But to me, it's like yeah, that's quite mysterious, especially as a beginner. How would you know what constant to set it to? So you set it as a normal constant and solve things as normal, even though it makes things a little bit ugly. If you want, here you can feel free to invent a new symbol and call this alpha or lambda or whatever. Yeah, as long as it's not a confusing thing, it's fine. But I'm going to stick with it. I'm perfectly comfortable with fractions and square roots. Okay. So now you can check the boundary conditions 2 and 3 would imply lambda equals 0 and lambda larger than 0 would imply both of these cases. It would imply x equals to 0, which means theta will be trivial. Again, these are standard Sturm-Liouville things. You can already see it quickly. Plugging in little x equals to 0 means b needs to be 0 from boundary condition 2, and boundary condition 1, you plug in 1, which means a needs to be 0. So both a and b needs to be 0. These are exponential functions. Just plug it in, you'll find that it's impossible to satisfy as well unless both c and d, capital C and D are 0. So it's only possible to, if you get sine cosines, now you can get non-trivial solutions. Focus on that. So for this case, we will apply the boundary condition x0, right? So x0 is plug it in there, cosine, yeah, so I have an e plus 0. And I want, so boundary condition 2, I want x0 to be 0. So I want this to be 0. And so e is 0. And then boundary condition 3, that's x1. E is 0. So now just f times sine of square root of negative lambda over 4 times 1. And I want this to be 0. Then we do the whole Sturm-Liouville thing. I don't want f to be 0, so I can divide by f, because if f is 0, it defeats the purpose. I just get a trivial solution. Again, so for non-trivial solution, I need the sign of that surd to be 0. 1, 6, sine of this to be 0. And which means the interior of this, you want it to equals to any integers of pi. That will make sine 0. And I'm going to skip the algebra. It's going to, so you want lambda to be negative 4 n pi squared. So now you have your eigenvalues and your eigenfunctions. The eigenfunctions, you don't really even need the f. You can drop that because any scalar multiplication of that is also an eigenfunction. Okay, so that's the x. Now for t, to solve for t, that's an exponential function, right? So hopefully you recognize it immediately as well. So the t equation means there's only one general solution. What are my constant A, B, C, D, E, F, G, into the lambda T. If you don't have a lambda, T dash equals T, you know the answer is an exponential. So the only function that's derivative is itself is e to the power of little t. And the chain rule, if you need a lambda in front, you need to put a lambda there. That's the chain rule. You can solve it properly, but this is just so common that you can report this. And right, so now we put in the boundary conditions. So we can't directly put in this yet because this has a function of x in there. So we piece this back together first. So at the moment, originally it's x of x times t of t, right? So because it's something I could do, right? The lambda is solved. So technically this lambda is minus 4m squared pi squared t if you want. Okay, so now you can piece it together. There's a lot of solution depending on what your n is. So we can sum either from 0 or 1, but 0 would just disappear over there. And you have basically some constant times sine nx times e to the minus 4 squared pi squared t. Okay, and then we do the last thing to try to find the k by using the final boundary condition, and we do the projection thing either by inner products or specifically multiplying orthogonal combination of that. So boundary condition 1 is plugging in. The boundary condition 1 is x0 equals to 2 minus 4x. I'll probably not be able to finish this, but I will write down the answer for you to check. So multiply by the orthogonal combination and integrate from 0 to 1. The left-hand side would basically give you km delta nm, which after you sum this, it would just be km. And the right-hand side will give you 2 over, so you can check this, 2 over m pi, 1 plus negative 1 to the power of 10. And the whole solution is done. I will write out the whole thing. That would be theta. In fact, I'll write out for u. You have the 4x minus 1, that's steady state, plus the theta part. Yesterday, the kn, I forgot to change the m back to n, so today I'll make sure to do that. It's 2 over n pi, 1 plus minus 1 to the power of n, sine nx to the minus 4 squared. Someone yesterday said I should put an extra bracket here, but anyway. Okay, so that's your kn, that's your xn, that's your tn eigenfunctions, and that's the u steady state solution. Okay, all right. So I think this will be well prepared for you to read the rest of them yourself. There's just other examples are just variations of this, and you'll see more examples tomorrow with Andreas. And hopefully have a great Christmas, great winter holiday, and see you after the break.